These diagrams are similar to those in the last video, but they're not exactly the same. Notice that the copper tube and the nichrome tube have been removed, so the electric current is free to flow from one terminal of the battery to the other. But we have different types of batteries. We have 1.5 V or 1.5 volt battery on the top, and we have a 3-volt battery on the bottom. Notice that the bottom diagram shows the light bulb brighter than the top diagram, and we also see that we have different currents on the top and the bottom image. So there's some relationship here that we need to look into. The battery itself stores electrical energy in chemicals. There are chemicals inside the battery. The battery and the energy is stored in the chemical bonds of the chemicals in the battery. When you create a circuit by attaching the positive end of the battery to the negative end of the battery, usually with some kind of a load in the middle, like a light bulb or a motor, then electrons can move from one end of the battery through those components, through the whatever loads you put in there, to the other end of the battery. When you if you roll a ball down a hill, okay, the ball has a certain amount of potential energy at the top of the hill, and then at the bottom of the hill, it has less potential energy. We have the same sort of situation with a battery. We have a certain amount of potential energy on one terminal of the battery and a different amount of electric potential energy on the other end of the battery. The difference between the potential energy on the different terminals of the battery is called the electric potential. We also refer to it as voltage. Okay, so these are things you certainly want to put in your notes. Voltage is the electric potential. It's the difference between the electric potential energy of one terminal of the battery and the other terminal of the battery. This is analogous to the difference in the height at the top of the hill and the bottom of the hill. So that is what the height difference is what is going to propel the ball down the hill. It's what's going to allow gravity to pull the ball down the hill, and the electric potential or the voltage is what propels the current through the circuit. In these two images, we see that the 3-volt battery has twice as much current as the 1.5-volt battery. So what does this tell us about voltage and current? You should be able to conclude that voltage and current are directly proportional to each other. If you double the voltage, then you are going to double the current. If you have half the voltage, then you have half the current. And this is going to hold true. If you triple the voltage, you have triple the current, and so on. In a circuit, the electric field points from the positive to the negative terminal. We've already learned about electric fields. And remember that an electric field is the direction of an electric field is determined by which way a positive charge will move when you put it in that field. So in a circuit, if you put a positive charge in the circuit, it's going to move from the positive terminal of the battery to the negative terminal of the battery. And so this should make sense if you compare this to the idea that like charges repel and opposite charges attract. The current in the circuit depends on the voltage of the power source. We just established this on the last slide. So the current is measured in amps. The voltage is measured in volts, or the electric potential or potential difference is measured in volts. And so the more volts there are, the more amps there are. The higher the voltage, the greater the difference in the potential energy of each electron between the two sides of the battery. Again, let's go back to the hill analogy. The steeper the hill, the faster the ball will roll down it. Remember, current amps are a measure of the current, of the flow of electricity through the wire. So the greater the potential difference, the more that current will flow through the water. So here we see just a conceptual problem. In one circuit, the terminals are at 98 volts and 100 volts. In a second circuit, they are at 2 volts and 6 volts. Which do you think produces a stronger electric field, and why? Well, let's look at the potential difference of each circuit. In the first one, we have a potential difference of 2 volts. 100 volts minus 98 volts is 2 volts. So we have a 2 volt difference between the two terminals. In the second circuit, we have a 4 volt difference. 6 minus 2 is 4. So we have a 4 volt difference between the two terminals. Which one produces a stronger electric field? Well, it might not be what you would have originally guessed. The second circuit actually produces a stronger electric field because the potential difference between the two terminals is larger. Let's go back to the hill analogy. If you have a ball rolling down a hill, what matters is the difference between the top of the hill and the bottom of the hill. So if you have a ball rolling down a hill, that a 4-meter hill that is near sea level, it's going to gain more speed. It's going to have more energy, more difference in energy than if you have a ball that rolls down a 2-meter incline that's at the top of Mount Everest, right? So what's important is the difference between the two terminals. It's not the absolute voltage. Here we see a marble track, and this takes the hill analogy a step further. On this marble track, we put the marble at the top of the track, and the gravitational potential energy is at its maximum point. As it rolls down the hill at each step, it decreases. The gravitational potential energy decreases and the kinetic energy increases. So think about a charge carrier. And again, a charge carrier it can be an electron or it can be a charged ion. It's anything that has charge and moves through an electric current. So a charge carrier or moves by an electric current, moves through some kind of medium. So a charge carrier moving through an electric field is in a lot of ways similar to an object falling under the influence of a gravitational field. We see a change in potential energy, and that change in potential energy is going to help us describe both the rolling of the ball down the ramp and also the motion of the charge carrier, or the effect on the charge carrier moving through the electric field. In this marble track, we see the potential energy depends on the height difference between the top and the bottom of the track. It doesn't matter, again, if you put the marble track on the floor or on a table. What's important is the difference between the top of the track and the bottom of the track. That's what determines the potential difference, the gravitational potential energy difference. And that's what's going to determine the voltage of a circuit, is the difference between the potential energy of the two terminals.